Back, CHEM200. I hope you are all well during this very strange time. We will try and get back as normal as possible. What that means, of course, is welcome to class. You got announcements. Homework, as you maybe have been aware, is still out there and posted, so you can get started on homework. Office hours will start next week using Zoom. You'll be able to connect to the meeting on 9:35 a.m. on Monday and Wednesday. We can focus on CHEM200 topics. We're adjusting the schedule. You can see quiz 3, exam 2 are after spring break. Please note I have posted grades on Canvas, so you can see those there. What we're going to do in these slides is we can't get away from the class theme, so I'll just mention the class theme. We'll talk about covalent compounds, and then we'll get into a lot of calculations with mass percent, empirical formulas, and combustion analysis. So here's the plan for next week. Monday, chapter 4, Wednesday, chapter 5, and then spring break. So you can just imagine the music for the Olympics right now. One thing I want to point out is reevaluating goals, reevaluating how to think like an Olympian. So I have no idea what your situations are like at home, but you might need to readjust. What does it mean to have personal goals for the remainder of this semester? Encourage you to make them challenging, but realistic, and then share your goals. And then if you don't meet a goal, see that as a learning experience that you can move on from. So you may recall we were naming, so this was a lot of qualitative nomenclature work, and this is where we left off. You can see here we have ionic compounds, some are type 2, metals with variable charge, some type 1, main group metals, 1 charge, many of these on here, polyatomic ions, those are posted on Canvas. So you can see we were in the metal, nonmetal, or more appropriately, the cation and anion compounds. That's where we left off. The new piece we added was hydrates. This was the only new piece in ionic compounds. So that means water is trapped in there, and the hydrate versus the anhydrate has different properties. So we talked about the naming of those with the prefixes here. And these are the questions that we left off last time we were together. So we just finished then is naming ionic compounds. So now where we're headed is to the covalent or molecular compounds. That's very different naming scheme, but also very different conceptually what kind of compound. So remember, that's the very starting point. Is this a covalent compound or molecular compound? Or is this what we've been doing? Is it an ionic compound? In this case, covalent compounds are sharing electrons. So sharing electrons, that means they have bonding pairs. I encourage you to think about the ones that you know. Right off, we can think about water, and that is a bonding pair between oxygen and hydrogen. So we know this. It looks different than the ionic compounds that we've seen, and now we're just putting the nomenclature that we have bonding pairs here, and we have lone pairs on the oxygen. So that's better at looking at it, what you've seen. You can see I've also drawn it already as a bent shape. We'll get into shapes later on in the next chapter. If we're sharing electrons, you've seen in the past, you can share single bonds, double bonds, triple bonds. These are the ones that we'll look at and talk about. And recall how many electrons that is. So a nitrogen triple bond, that's 6 electrons. Oxygen double bond, that's 4 electrons. And we already drew water with 2 electrons for each bond to hydrogen. So that's sharing electrons. These right here are Lewis structures. Remember, for ionic compounds, we drew Lewis symbols. So the symbols were the cation and the anion with the electrons present and the charge. So top right, Lewis symbols, sodium chloride. All of these down here are Lewis structures. What we don't want is a mix of this Remember, sodium chloride is an ionic compound made up of ions. It is not sharing electrons. So now we're talking about covalent compounds. Starts with the covalent bonds of the diatomics. So the 7 ones you need to commit to memory. This looks like a 7 over here. The halogens, oxygen and nitrogen, that's 6 of them. And then hydrogens are 7th over here. Molecular compounds are not only different the way they bond, but their properties are different. So if you look here, this figure is showing pentane going from the liquid to the gas phase, and it does that fairly easily, and that's because covalent compounds have low boiling points. So low boiling points are all about the intermolecular forces. And that's a topic that we'll get on to at the very end of the semester, and you probably saw in Chem 152. But covalent molecules hold the covalent bonds hold the atoms together. Intermolecular forces hold the individual molecules together. So different terminology there. Start with examples that you know, of course. CO, CO2, that is carbon monoxide. There's no prefix on the first one if it's a 1. Second one has to have a prefix, so carbon monoxide, carbon dioxide. There's the rest of the prefixes here. The examples now, you start with those simple prefixes. The second element ends in "ide." Then you can pause this video and do these examples. So we can take a look here. First element, in this case, needs a prefix and is not "ide." The second one needs a prefix, is an "ide," and "dec" is the prefix, but because it's with oxide, we put it and we drop the "a," decoxide. Carbon monoxide, carbon dioxide, we already talked about. Chlorine, no prefix, there's only one. Trifluoride, you can see here. Phosphorus pentafluoride. And we also can have sulfur hexafluoride. This is similar to helium gas. You know, helium gas makes your voice really high and funny. Sulfur hexafluoride does the opposite. It makes it really deep and intense. You can look up Mythbusters video for that if you want to check that out. Nitrogen triiodide and nitrogen dioxide. So that's formula to name. So you can go ahead and pause, go from name to formula. As you see here, prefixes tell you how many. Sulfur dioxide, nitrogen monoxide, and so on. Before we could see patterns with ionic compounds, sodium chloride, lithium chloride, they had the same formula. Here, there are no patterns. Nitrogen and oxygen, 1 nitrogen, 1 oxygen. Down here, 2 nitrogens, 1 oxygen. There's another compound, 1 nitrogen, 2 oxygen. So there's no patterns like the ionic compounds that we saw before. So what we've done then, remember we spent the majority of our time over here with ionic, and that was type 1, metals that only form 1 ion, type 2, a variable charge. There's some examples here for you. The hydrates fit into both of those compounds, and then we've just named the molecular, and we have the examples here of diphosphorus pentoxide. So that is the summary of our naming compounds. We will get to naming some acids. That'll come later when we get to acids in the chapter. But this is the qualitative piece. We have to know the names of these substances to work with them. So what are we going to do with them? It's all about the quantitative now. So grab your calculator, make sure you're ready to go here. Formula mass, you may recall, we have a compound, in this case, hydrogen peroxide. Number of atoms of the first element, that is 2. And we look up the atomic mass of hydrogen, and I'm going to use for that 1.008. And then we have 2 oxygens, and I'm going to use 16.00 for that. And what we're doing here is calculating the mass of the compound in AMU. So regardless of the compounds, maybe you have glucose, doesn't matter how complex you get it, you do the same thing for all of this. In this case, it'd be 6 times the atomic mass of carbon, 12 for this hydrogen, 6 times that oxygen. And you just keep adding and adding however many atoms you have. So now what we're looking at is what we can translate into the lab. We want the mass, grams. So it's the same units, the AMU, it's just now grams per 1 mole, okay? So sorry, it's the same number. The number stays the same of the molar mass, but the units go from AMU to grams per mole. So that's what we're using, and we're going to use that to go from grams to moles. Sorry about that. Grams to moles, or from moles to grams. So we've got to be familiar with how to calculate the molar mass and how to use the molar mass. And we'll do several of those on these slides. So first one, 50 grams, and a good review is what's the name of this compound? So in that case, you would need to think about the charge of oxygens, -2. And there's 2 of those, so this is actually lead-4 oxide. So how many moles are in 50 grams of lead-4 oxide? So if we have our grams, and we have our grams per mole of each individual elements there, we can then go to moles. And you can see that works out here for you, 50 divided by the molar mass, and sig figs, 3 sig figs, 3 sig figs, all that to keep in mind. So that's grams to mole. Next one, we're now taking a look at our units, thinking about where we're at. This is the roadmap. Grams, moles, particles. So we have to recall that if molar mass got us between grams and moles, that's Avogadro's number to get us between moles and particles. So if we set up the problem, you can see that if we have molecules, that's a type of particle, and the reason we call it a molecule is because it is a covalent compound. We could name that compound nitrogen dioxide now. And if we go from particles to moles, that's Avogadro's number here. And then what we just did was grams to moles. Now we're going moles to grams. Units cancel, and again, check sig figs for that. So you want to be really comfortable grams, moles, particles, particles, moles, grams with this stoichiometry. So take a look here. If we're looking for the largest number of molecules, and all of these are given in mass, remember, if we're going to molecules, we're going to use Avogadro's number, but first we have to go through molar mass. So molar mass, if we think about it, we're dividing by molar mass, so it's the smallest molar mass gives us the largest number of molecules. All of these have a greater molar mass than this methane or carbon tetrahydride. Another example of grams of sodium are in 6.2 grams of sodium chloride. So here is now a chance to change from moles of sodium chloride to moles of sodium. So we've been talking about the roadmap. Grams, moles to particles. Well, that's of one substance. So we can call this substance X. Moles of X, particles of X, grams of X. So that's where we need to know molar mass, Avogadro's number. But now what we're doing here, this is going to be critical for this chapter, is converting to moles of something else. That's moles of Y. So in this case, that was moles of sodium chloride, moles of sodium. We had to use the mole ratio here to change that. And in this case, if we're going sodium, sodium chloride, I know the units or the number doesn't change, but it's the unit. So you can see here 1/1. That's not going to change your math, but moles of sodium versus moles of sodium chloride, that's a big deal. Are you going to go have your lunch and eat grams of sodium? Of course not. That would be terrible. That would be painful. You're going to eat grams of sodium chloride. So this is making sure we're converting. That's that mole-mole ratio. And then you can see we account for molar mass or significant figures. So what's next on this topic is mass percent. Okay, so we've just been dealing with grams, moles, particles. Now we're completely in mass, and you can see it's the mass of some element that you're interested in over the total mass. So I encourage you to look at this and be able to say, what is the calculate the mass percent of hydrogen? So that's the mass of hydrogen, because there's 2 of those in water, times the molar mass, divided by the total. Same thing for oxygen here. So if you take a look, we've got 1 oxygen, that's 16 grams, divided by total, and all of these are coming from the periodic table, so your sig figs, you could carry this out, 2, 3, 4, in this case 2 is fine. You can see because of the rounding and everything, it's not going to be exact, but if it's a 2-component system, oxygen, hydrogen, it should be around 100%. So we get to the next problem, and you can pause it if you want to do this before I show the answer. It starts with knowing the name though, calcium nitrate. So we have to recall calcium, 2+, nitrate, polyatomic ion, on canvas, one of the ones they need to memorize. That only has a -1 charge, so you need 2 nitrates for this calcium. That affects the percent. So total molar mass 164. And then you can see you count for 1 calcium, 2 nitrogen, and 6 oxygen, get you to 100%. You could do this for anything. We've got chlorophyll. This is ridiculous. This is a massive compound. Doesn't matter. You can still figure out what's the percent carbon, hydrogen, and so on. So the main thing, the takeaway from these slides is when it says calculate mass percent, you know it's the mass of one element over the total, and then you could get that for each element in this. So here's how we're going to use mass percent though. Okay, we have benzaldehyde, and it's given 79.2% carbon. What mass of benzaldehyde contains 19.8 grams of carbon? So if you're starting with 19.8 grams of carbon, you need to see this percent as a ratio. So that's 79.2 grams of carbon, and percent, means per 100. So this is actually per 100 grams of benzaldehyde. This is your conversion factor. So if you start with grams of carbon, then you need to decide, am I multiplying by this conversion factor? Am I dividing by this conversion factor? So I encourage you to pause, set up, and solve for mass of benzaldehyde. You can see here what's done is the conversion factor is inverted from how I wrote it. Grams of carbon cancels because you were interested in how many grams of benzaldehyde is left over. So quick review, we named a lot of compounds. Now we started some calculations. Mass percent, we saw the grams, moles, particles. Now we're going to something that maybe seems familiar from Chem 152. That's calculating empirical formulas. This will be in experiment 6 in lab, if you have lab at Miramar. So you'll get plenty of opportunities to do calculations there, but here's a review. You started with mass percents, and maybe you start with mass. However you start, you need to get to moles. You got to moles, then you want to get to the ratio of moles. So you divide by the lowest moles, and that gives you your subscripts. You may have to do a calculation to get into an integer form. So assume 100 grams of a substance if you're given percent. Calculate the mass of each element. Convert to moles. So what we've just been doing, grams, use the molar mass, go to moles, and divide by the smallest mole value. Many cases, students will be in mass and divide by the lowest mass value, but remember, formulas are about moles, so we have to be in moles first, divide by the smallest value. Then multiply each number by an integer to obtain whole numbers. So let's get to it. How I would encourage you to look at this problem is if you have percent, right away think, I need to convert that to grams, okay? So that's 74 grams of carbon, that's 8.70 grams of hydrogen, and that's 17.3 grams of nitrogen. If you've got that step, then you can go through the steps from the previous slide and go grams to moles, divide by the lowest moles, multiply to get whole numbers. So go ahead and do that now. Take a look what we just said. Go to mass, divide by molar mass, critical step, we have to be in moles. And then we have to look and find the lowest moles. So you can see here, I've put in all the moles as subscripts. Of course, that's not how we write formulas, right? We want whole numbers. So 1.23, that gives you 1, that gives you 7, and that gives you 5. So that's the empirical formula calculation for nicotine. If we take a look at the next one, we have vanadium oxide. So vanadium is transition metal, so we don't know which vanadium is that. We have to solve for the formula. So this is a good example. You'll do an oxide, magnesium oxide in lab, but this is a good one of, we don't know just by the name, so we have to convert to grams. We have to convert to moles, and then we divide by the lowest. Okay, and then this is the big red flag on this slide. That's not how we write formula. So we multiply that by 2 to get 3. If we multiply this one by 2, now we've got to multiply this one by 2. So that was quite easy to see, 1.5, let's get it to a whole number, multiply by 2. Others aren't quite so easy. If you think in fractions, 1/4 needs to multiply by 4, then maybe, or 1/5 needs to multiply by 5. But this figure is really helpful with this to say, do I need to multiply, do I not? Please note, if you get something like 1.66, that does not mean round it up to 2, okay? And this rounding is a really big deal. So we need to think first, is it something to round? Well, if it's 1.98, yes, round that to 2. If it's 1.66, 1.75, Now you can see we're not rounding, we have to multiply to get the formula. So here's a little more complicated problem. Okay, remember our first point is to get to the mass of the elements. Okay, so we have the mass of titanium. It's heated with chlorine gas, and it gives you the mass of what? That's the compound. Okay, so we need the mass of the elements. So think about how you're going to do that. That's conservation of mass. So figure out the mass of the elements and then solve for the empirical formula. Go for it. What I want to point out here are two ways to do this problem. So this first one, I really don't like this method, okay? I want to show it to you because we say chlorine gas. Well, previous slides, you know chlorine gas is a diatomic. So we've got the mass of titanium and we've got the mass of chlorine gas. We do the same thing, molar mass. Take a look, molar mass here for the diatomic is 70.9, but you have to put in the formula in this way, Cl2, because that's what you use the mass for, the diatomic. That makes it a little bit awkward. I don't like this way, but I wanted to show it to you. So you get the ratio, that's 2. 2 times 2 is 4. You can do it this way, go for it. What I would do, I know we don't have single chlorine atoms as chloride or as uncharged here, but I'm saying this is chloride. This is just the total from the element chlorine, so that's 2.12 grams. So here you can see the molar mass is 35.45 because that's only one chlorine. Now I don't have that strange subscript to deal with, and you can see I still end up with the same 1 over here, and that gives me the ratio of 4. That's the way I'd recommend it, but both are available to you. So we got our empirical formula. Sometimes we can get more information to get the molecular formula. So if we have a multiple of the empirical formula, so it's some factor of the empirical formula, and that molar mass is given, we can calculate the empirical formula molar mass, and then it's a ratio of that. What I mean by that is the molecular formula over the empirical formula is some whole number. And that's the number that you multiply the individual atoms by. So let's do an example and see that. So benzopyrene, we don't know the name of that, so we can't get the formula ourselves, but it has an empirical formula of C5H3. We want the actual molecular formula of benzopyrene. So we know the molecular formula of the molar mass of the empirical formula. We can calculate that, and we're given the molar mass of benzopyrene. So you can see those are not going to be the same. If we just look offhand, carbon's 12, that's 60 if you have 5 of them, hydrogen's 1, so that's 63. Those are not the same. So we need to take a ratio of those two, go for that, and see if you can come up with the formula. See, ratio equals 4. Then we're not done. That's not the answer of the problem. It's 4 times 5, 4 times 3. That's where we get the molecular formula there. You can go from the very beginning. So in this case, look, you're given percent. That was mass percent, go to mass, go to moles, divide by the lowest moles, eliminate any decimals, and now you're also given the molecular mass of dioxane. So now you can do the molecular formula of that. Go for that. That's all the steps. What I want to point out here is you calculated the empirical formula, C2H4O. Remember, the empirical formula then gives you the molar mass of the empirical formula. You know that, and you can see it's by a factor of 2. So 2 times 2, 2 times 4, 2 times 2, That's how we get the final answer. Aspirin you're actually going to synthesize in lab in CHEM152L, or you synthesize it in CHEM152L, so you can look at that. And actually, when I referenced the experiment 6, the magnesium oxide, that was a CHEM152L experiment as well. So here you can take a look at this one, and you got the molar mass and calculate the molecular formula of aspirin. Lastly, I mentioned CHEM152L a couple of times in CHEM152. This is how CHEM200 is different. This is the 2 slides that are different from CHEM152, but there's a lot going on here. So combustion analysis is done for calculating empirical formulas of compounds that contain carbon, hydrogen, and other elements. So when I synthesized compounds, I had to determine what elements were in my compounds, what were their ratios, what was the empirical formula. This is one way to do that. Send it off for combustion analysis. So what they do is they burn it in O2. All the carbon becomes CO2, and all the hydrogen becomes water. So you can see the process down here. These are weighed, and it's determined how much water was added, how much CO2 was added when this sample was burned. So that's different than telling us how much carbon was created or how much hydrogen was created. We're saying water and CO2. That's the difference with combustion analysis. So in this problem now, big red flag is combustion analysis. This is not just mass of elements that you convert to moles. Okay, so you're given a sample of tartaric acid, and this is contains carbon, hydrogen, and oxygen. It was combusted. Please note, look at the mass here, 14.08 grams of carbon dioxide, 4.32 grams of water. Find the empirical formula of this. Well, remember, if we're going for the empirical formula, we need the mass of the elements. So that brings into the very beginning of this slides, how do you go from grams of carbon dioxide to grams of carbon? How do you go from grams of water to grams of hydrogen? We need all of that information. So grams, and then you're going to see we still need the grams of oxygen. So we have grams of carbon, we have grams of hydrogen. If we have a 12 gram sample, then we can get our grams of oxygen. And then where do we go from there? It's an empirical formula problem. So it's grams, moles, same process as you've seen. Go for it, give it a shot. You can see here, molar mass, grams carbon dioxide, that gets you to mole-mole conversion, that gets you to moles of carbon. So we need to know the moles of carbon, that's important. We also need the grams of carbon, so I've done that here. Hydrogen, take a look here. There's 2 moles of hydrogen for 1 mole of water. So in this case, the moles of carbon dioxide, moles of carbon were the same. In this case, moles of water, moles of hydrogen are not the same. So we need moles of hydrogen, and we need grams of hydrogen. Mentioned earlier, if you're going to get the grams of oxygen, conservation of mass, you can start with the mass of the compound minus the mass of carbon minus the mass of hydrogen. And in grams of oxygen, now you can get moles. Great. If we got moles, that's an empirical formula problem. Moles divided by the lowest, that gets you to the empirical formula is C2H3O3. If you were given a molar mass of a molecule, then you could have done that ratio to get the molecular formula. That would have included everything, but I wanted to show the piece here of combustion analysis. The last slide here is what things are combusted. Many of you will go on to organic chemistry. This is just a list of some organic compounds here you're familiar with. Methane, that's in the Bunsen burners in our labs. Propane, maybe you've grilled with. And then you can see a variety of other ones as we have here. So this concludes our chapter 4. and I hope to see you on office hours.